All right, Matthew, here we go. We got lesson 5.2.2, completing the square. All right, we've already learned two methods for solving quadratic equations. We use the zero product property. So that's when we were like factoring, and then we set our factors equal to 0. And then the last lesson, we were solving by taking the square root from both sides. Now that requires a perfect square being there, so it works sometimes. So let's look at this problem. On this problem, I've got x squared plus 4x plus 1 equals 0. Why is this difficult to solve with our known methods? Well, first of all, it doesn't factor. Because what multiplies, like if we did our diamond method and said 1 and 4, what multiplies to give us 1 but adds to give us 4? Well, there's no numbers that multiply to give us 1, adds to give 4. So I can't factor it. Therefore, I can't use the zero products property because that only works when it factors. Now, what about the solving by square root? Well, I don't have a square root. Remember we had perfect squares on this one? So we do like x plus 5 or something like that squared, and then we took the square root from both sides. Well, I don't have a perfect square over there. So I'm not able to use either one of these methods. So it doesn't factor. And it's not a perfect square. We'll call that a binomial square. So the two methods that we have so far are useless for this particular problem. So we need a new method. First thing we're going to do is look at this new method called completing the square and look at just kind of visually what we're doing. Now remember, we're dealing with squares. So let's say that I had x squared plus 4x plus 1. Now using algebra tiles, we might line it up like this. X squared here, 2 of the x's here, 2 of the x's here, and the one single there. Now this is not a square. So how many unit squares do we need to complete the square shape? Well, I'd need another square, unit square here, another one right here, and a third one right there. So I'd need 1, 2, 3 unit squares. Now in an equation, if I add a number to one side of the equation, I have to also add the number to the other side of the equation. So if I add 3 squares to this side of the equation, so right here, that means I have to add 3 to this side of the equation because equations always have to balance out. Now I've also made a perfect square because this is x and this is plus 2 over here. And this is x plus 2 singles right there. So we needed 3 to complete the shape. So now we've got x plus 2, because we made it a square shape here, squared. Because this was x squared plus 4x plus 4. And then we added 3 to the other side. So equals 3. And now we can solve it using the solving by square root method, where I can take the square root of this side and this side, boop, and get x plus 2 equals plus or minus, don't forget the plus or minus, the square root of 3. And then I would just subtract 2 from both sides and get x equals negative 2 plus or minus the square root of 3. And there's our two answers. So we now have a method that's going to work for that one. All right, so for this one, we're going to rewrite the following as perfect squares and then solve using that visual method that we just did. Okay, so this is almost a square. I need 1 square right here and then 3 more squares right here. So I need 4 extra squares. So I'm going to add 4 squares to this side, which means if I add 4 to this side, I have to add 4 to this side because equations always have to balance out. So this is x squared plus 6x plus 9 equals 4. We're balancing out the equation there. Now this side of the equation is x plus 3 of these singles, and this is x plus 3. So my area that I have here is a perfect square of x plus 3 squared. And then on the other side, we've got equals 4. So now we can take the square root from both sides. And we get x plus 3 equals plus or minus the square root of 4 is 2. I'm going to subtract 3 from both sides. And I get x equals negative 3 plus or minus 2. Now, since there's no radicals left here, I can actually give the two answers. Remember, one of them is going to be negative 3 plus 2. So negative 3 plus 2 is negative 1. And then negative 3 minus 2, which is negative 5. There's my two answers. By the way, this could have factored, right? Because what multiplies to give us 5 and adds to give us 6? 5 and 1. See how we're getting negative 1 and negative 5 over there as answers? It probably would have been easier to solve this one by factoring and then doing the zero product factory property, but oh well. All right, next one. Now this one, we have minus 5 on this side. So these white ones mean that we're missing 5. So I need to replace these 5. I need to add a 5 singles and one more to finish this off. So what did I do? I added a total of 6 to that side. So if I add a total of 6 to that side, I have to add 6 to this side. So what we have here is, x squared plus 2x, 6 minus 5 is plus 1, equals 6. Now this is a perfect square. This is x plus 1 over here, and it's x plus 1 over here because we added those 6. We made up for the 5 we were missing, and then we added 1 more. So that's a total of 6 that we put over there. So this is x plus 1 squared equals 6, and now we can take the square root of both sides. So we get x plus 1 equals plus or minus the square root of 6. And then I'll subtract 1 from both sides, and we get x equals 1, negative 1, plus or minus root 6. Did it. All right. Now we're going to do a mathematical method instead of having to use these algebra tiles or do that. This is kind of nice visually, but you're not always going to have algebra tiles with you. So let's look at the association between squaring and the sum that you get when you square it. So if you did the area model on this one where you have x minus 5 times x minus 5, you get x squared minus 5x plus 25. So this written as a sum would be x squared minus 10x plus 25. All right, let's do one more. Well, let's do 2 more. Let's multiply this one out. We got x plus 1 times x plus 1. So we got x squared, 1x, 1x, and 1. So this would give us a sum of x squared plus 2x plus 1. Whereas this one over here, if we do x minus 8 times x minus 8, we get x squared, negative 8x, and positive 64. So that sum is x squared. These two are like terms, so we get negative 16x plus 64. Now there's a pattern here for these numbers. This number here is this number squared. This number here is double this number. See that? Negative 5 times negative 5, 25. Negative 5 plus negative 5, negative 10. Same here. This number here is this number here is this number squared, and then we're doubling it here. 8 squared is 64, doubled is negative 16. So there's a pattern there. We know that when we have a perfect square, this number is this one doubled, and this number is this number squared. So here's what we can do. All right, if we're solving this by completing the square, what I would do first is number 1, I'm going to move the 5 to the other side. So I get x squared plus 4x. I'm going to leave a little blank here, equals 5. Now I want this to be a perfect square. Remember, this number was doubled and this number was squared. So if I take half of this number and square it, I should get the perfect square over here. So I take 4, cut it in half, and square it. So 4 cut in half is 2, 2 squared is 4. So I need to add 4 right here. Over here, I would also add 4, because if you add 4 to one side of the equation, you have to add 4 to the other side of the equation. Now, what perfect square did we just make? We made x plus 2 squared. Because this number is this number doubled, and this number is this number squared. And over here we get 9. And now we can just take the square root from both sides. So we end up with x plus 2 equals plus or minus, and then 3. Next, we would subtract 2 from both sides and get x is equal to negative 2 plus or minus 3. And then, since these are both integers, we can actually find the answer. Negative 2 plus 3 is 1, and negative 2 minus 3 is negative 5. There's my 2 answers. Over here, let's do the same process. Let's move the 1 to the other side first. Let's add 1 here, add 1 here. That gives me x squared minus 6x. I'm going to leave a blank right here, equals 1. So I want to make this into a perfect square. We're going to take negative 6, cut it in half, and square it. So this is negative 3 squared, which is 9. So 9 is the number that I need to add to both sides. Now, what perfect square did we just make? Well, what number did we square over here? We squared negative 3. So this is the perfect square of x minus 3. Because this number is this number doubled, and this number is this number squared. That was the pattern that we saw. And over here we got 1 plus 9 is 10. We can take the square root from both sides now. We get x minus 3 equals plus or minus the square root of 10. We're going to add 3 to both sides, and we would get 3 plus or minus the square root of 10. All right, we're almost there. Last problem. Okay, I am going to subtract 3 from both sides, and that leaves me with 2x squared plus 12x equals 8. Now here's a problem. I've got an a value right there. And all these other problems that we've been doing, they've got an x squared. I need to get rid of the coefficient in front here. So I'm going to divide everything by 2. And that leaves me with x squared plus 6x equals 4. Okay, everything's good now. I can continue on. So I'm going to take 6, cut it in half, and square it. So 6 cut in half is 3. 3 squared is 9. So what am I going to do with that 9? Remember, we add it to both sides. So I get x squared plus 6x. I add 9 to this side. Over here I've got 4 plus 9. So I added 9 to both sides. That completes the square over here. This is now the perfect square of, what did we square? We squared 3. So this is x plus 3 squared, because this number is this number doubled, and this number is this number squared. That was the pattern we saw. So over here I've got 13, and now we take the square root of both sides. and we end up with x plus 3 equals plus or minus the square root of 13. Last step, subtract 3 from both sides, and x is equal to negative 3 plus or minus the square root of 13. The end. Sweet dreams. Bye-bye.